Hello students, welcome back. In the first video we did part A, 1A and 2A. In the second video we did part B, 1B and 2B. As for part C, 1C and 2C, there's nothing to talk about as a matter of fact because we did far more than just two balls in part A. Just the use of multiplication rule. And of course I changed accordingly, so this is not the answer for the homework problems, but you can get back to that. We want three balls without replacement, all red, so 6, 5, 4 dropping, 15, 14, 13, and again it's multiplication rule. Down here, no drop there because this is with replacement. So second and third rows are exactly the same as the first row in terms of probability, in terms of the number of balls and color distribution. So they're independent. So we use what? The multiplication rule 3 times with identical probabilities. So what do we have? We have repeated multiplication or the power. That's about it. No problem there. And finally, let's go to part D. Here we go. 5 balls are selected without replacement versus with replacement, all right? And then we have 3 red and 2 blue. So this is more complicated than part B. 3 red and 2 blue. What are the probabilities? What kind of arrangement I'm going to get? 3 red, red, blue, blue, blue. That's one. And red, blue, blue, red, blue, that's another. And then red, blue, red, red, blue, blue. I have a problem. How many are those there? And how do I exhaust all the possible order? And as for the probability of individual sequence, it should not be that bad because multiplication is commutative. As you saw before, each sequence will give me just one same probability because it's basically rearranging the multiplication of the numerator, 6, 5, and 4 in this case, and then the denominator, 15, 14, 13. All the same, fine, but how many are there? That's a bit problematic here. Well, we have to consider this, how to arrange 3 red and 2 blue. I have only 3 choices there, and how many more, it's a little bit hard to tell, and that's something we'll have to discuss. But then again, I'm not going to do the same thing as homework problems, so let's change this a little bit. If 7 balls are selected with replacement versus without replacement, okay, instead of 5, let's go to 7. And then what is the probability? We get 3 red balls and, okay, 4 blue balls in any order. Okay, let's do that. 3 red and 4 blue. So this arrangement is going to be a heck of a lot more complicated. So we'll have to rely upon a formula. And of course, how to derive that formula is going to be a big topic. I talked about it in my lesson video, main lesson video, but what can I say? It's long and complicated here, and I don't want to reproduce that here. So without any further explanation, I'll just give you an explanation. Without any further explanation, excuse me, I'll just give you the formula. So we have 3 red and 4 blue, right? Okay. 3 red and then 4 blue. And then there are many different types of arrangements there. And it's going to be this. How many arrangements are there to arrange 3 R's and 4 B? R, B, 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 B. There's one, but there are a heck of a lot more. And then that's going to be the repetition as we saw before, basically this part. And then times I have to get appropriate probability. These kind of thing, but they're all the same because multiplication is commutative. So all I need is, let's see, 6 out of 15, all right, and then 5 out of 14, and then 4 out of 13. That covered 3 red, and then 5 out of 12, and then 4 out of 11, 3 out of 10, and finally 2 out of 9. Did I cover 3 red and 4 blue? Yeah, I have it. And then what if we have in different order, just like the previous problem? All I have to do is to rearrange this multiplication. The denominator will stay as 15, 14, 13, 12, 11, 10, and 9 because that's the number of balls left total. And then the numerator will be 6, 5, and 4 for red, maybe in different order, and 5, 4, 3, 2 for blue, quite possible in different order, as you saw over here. And all kind of different orders, how many are there? And that's something that you have to figure out over here. Okay, what are the number of arrangements are there? And that is called a combination, total 7, and choose 3. So out of total 7, if you select 3 slots for red, the other 4 will be automatically blue. So whether you choose 3 or choose 4 will make no difference. They'll turn out to be the same. So combination 7 choose 3 or binomial 7 choose 3. Either way, they mean the same thing. The notation I personally prefer is B. Binomial 7 choose 3. This is what I like. What is the preferred notation of our textbook author? Let's go a little bit general and choose R. Combination and choose R. This is my second preferred. Out of N, choose R. I think this is a notation our textbook author is using. I don't like it very much, but there they are. And then there may be even more different ideas here. In any case, here's a formula. N factorial over R factorial times N minus R factorial. So this is 7 factorial, that is 7 times 6, 5, 4, 3, 2, 1, all those multiply. Over, I'm selecting 3, so 3 factorial. 3 times 2 times 1. And then 7 minus 3, so 4 factorial. And then that's something you can calculate with your calculator. Of course, you can do it with paper and pencil computation with clever cancellation. But if you use calculator, you're going to get something. And plug that something over here. Well, let me reproduce that here. And that is this. And then use your calculator to calculate this thing, and then you're gonna get what you want. I wanted to put question mark here. Okay, all right, and let's align all these equalities. So that's how you can get the answer. By the way, 7 choose 3, and then 7 minus 3 is 4, this one. And 4 factorial, 3 factorial, that's the same, isn't it? It should be the same. Yes, that's the same, isn't it? So let's get back to 7 choose 3. So 7 choose 3 and 7 choose 3 Okay, all right. Versus 7 choose 4. I don't want this notation. Even though that is preferred notation by our textbook author, I really hate that. So all I did is changing the order of multiplication of the denominator. If you go back to this formula, so choosing 3 slots out of total 7 versus choosing 4 slots out of total 7, they're the same. If you choose 3 slots, the other 4 will be automatically blue. And then if I choose 4 slots for blue, and the other 3 will be automatically red. So they have to be the same. In general, of course, I'm going to get this notation and choose R, and that is N, and that is R, and this one is N minus R. And then that is the same as N choose N minus R, and then N choose N minus R. So whether you call it binomial NR or combination NR or N choose R, they all mean the same thing. They mean this quantity here. Okay, all right. That was for without replacement. And I have to admit that this formula is not very important formula. It just works as a stepping stone for the next one, which is important. Okay, all right. Let's go down over here. 7 balls are selected with replacement, this time with replacement. What is the probability we get 3 red and 2 blue? So 7 choose 3, so out of total 7, take 3 slots for red, and then the other 4 will be blue. So arranging 3 R's and 4 B's. And then we don't have any of those drops, do we? They all remain the same because we are doing basically the same thing over and over again. We are replacing all those balls back in. So denominators stay as total number of balls, 15. Oops. And then the numerator stays as the number of available balls at the start, because that never changes. You are putting all those balls back in. So what we have repeated multiplication. 6/15 to the 3rd power times 5/15 to the 4th power. So that's red and that's blue. I can put everything in the same line here. Okay, that's easier to see. And then we can calculate this binomial 7 choose 3 using, this formula. Or in general, you're going to get this. So the probability is binomial N choose R times the probability of the first, probability of the rest. Factorial over R factorial times N minus R factorial, that's the formula, and P to the rth power times Q to the N minus R power. So basically, this event, red, is taking place R times, and automatically N minus R times blue is taking place. And then how many total arrangements are there? And number of arrangements of those 2 characters. And that thing is called binomial. Bi means 2. So this is called binomial formula. There are many binomial formulas out there, as a matter of fact. This is one of them. So this one is a little bit more important, and important enough that it may show up in exam. This one, almost no chance. There are plenty of other important things here, like multiplication rule. Yes, okay, that's important. But as for this formula, this binomial arrangement without replacement, there's a formidable name for that, hypergeometric. And I don't think that's really important for students here in this level. But the next one here, with the replacement case, this one is to a certain degree important. And the name of this kind of event is called binomial event, binomial trial, or, well, it has many names. So how to use this kind of circumstance? Well, let's see. And let's suppose we have an election model, and then we have a group of people, and then 30% of those people. No, excuse me. What am I talking about? 6 out of 15, that percentage of people support candidate 1, and then 5 out of 15 people support candidate B, and then there are the rest. And then if I select 7 people at random, and what's the probability we have 3 people who support candidate A and 4 people who support candidate B, kind of thing. We have this kind of situation. I'm still not convinced that this is realistic. I don't blame you, because how do I know we have 6 out of 15 and 5 out of 15 to begin with? And from there, we are doing this kind of prediction where you can always check by actually selecting 15 people. The real use of statistics is going backward. You do the sample study with 15 people. Okay, that's a ridiculously small number. Not 15 people, but 1,500 people. And then we have appropriate probability distribution here. And then using those, we want to predict the actual support percentages of, say, Mr. Biden or Mr. Trump or whatever. And that's a kind of model we want to build. And the theory behind it is right here. This is what we use. So this one is to a certain degree important. But of course, more important part is the multiplication rule. There's no question about that. Multiplication rule here is more important at this moment. And then to a certain degree, please remember this binomial formula here. In general, it looks like this. And then this binomial arrangement, B and R, or combination and choose R, has this formula. N factorial over R factorial times n minus r factorial. I don't need this dot here. And then P is taking place R times, and Q is taking place n minus r times.